Then yeah, our next speaker is Matthias Sauzet, and he's talking about the curious case of case. So you can share your screen, yeah? Then
can you see it?
Please, yeah. So please go ahead.
Okay, thank you. So this will be a short talk about the curious case of case. So case analysis in a dependent type series, the one of Coq. And I'm going to talk about how to get a correct and efficient representation of the case analysis construct, both in Coq and its model in MetaCoq. And this is joint work with Mevenden Bertrand and Yannick Forster. Okay, so our overall goal in the MetaCoq project is to improve trust in the type checking of proofs in the Coq proof assistant, and to build a clear specification of the theory implemented by the assistant. And how do we do that? Well, we start from Coq's calculus, which is just reified as an inductive data type in Coq. So an inductive data type representing the syntax of the system and all the operations on terms. From that, we show an equivalence to an idealized calculus, which is called Pickwick, for polymorphic cumulative calculus of inductive constructions. And we show an equivalence between these two. So that's a change in representation to simplify the meta-theoretic study. And we show an equivalence with the calculus implemented in Coq. And for that calculus, we develop a full specification. And we show correctness and completeness of a verified type checker for this calculus, from which we can also derive an erasure procedure that goes to an untyped lambda calculus, from which you can compile down to other languages. So all of this is proven in Coq in the MetaCoq project. And today I'm going to focus on a very specific part of the proof of completeness of type checking for inductive types, with well-known or infamous dependent elimination rule for indexed inductive types. So here I'm writing basically elimination of inequality proof inside some type P, and that's basically the syntax you see in the kernel representation. You match on a proof, you give a name to it, E, that you're going to use to express the return predicate, so the return type of the elimination. You say that it must live in the EQ type. You don't mention the parameters at which equality is instantiated. So equality takes two parameters, the type and the first endpoint of the equality, and then it has an index, Y, that we name as well, and that we can use in the return type. This matches a single branch for the reflexivity of equality and returns a branch B. And the whole expression as type, the predicate applies to Y and P. So our work is really about how do we prove the actual code that is implemented in Coq. So we are using the same representation of this pattern matching as Coq is using. And there is a peculiarity for this match construct, that in the Coq kernel, the predicate is not represented simply as some arbitrary term P, but it must have a specific shape, which is some lambda abstraction on the indices of the inductive type and an object of this inductive type, so on Y and E. And this lambda abstraction must end with a term, which must have a sort type. Okay, and what we found out by when trying to prove completeness of our type checking algorithm for this representation was that the typing rule used in the kernel was actually wrong, that it was incomplete. It was doing the wrong comparisons of universes and of parameters in the kernel. So the confusion is basically that the typing rule in the kernel, when it sees a match, it first infers the type of P. So it infers that P is some inductive type applied to an inverse instance, here I prime, then parameters A prime and T, and some index Y. And then it looks at another annotation of the inductive type EQ, which is part of this return type annotation, which might have a different universe instance and different parameters, I and A, and then it must ask itself, how do I compare them? So should the universe instances be equal in some cumulativity relation, and same for the parameters. Should they be convertible? Should they be in some kind of cumulativity relation? What we found out was that the flow of information in the implementation was not really clear, and that this rule mixes typing and cumulativity, which is actually gives us evidence or some ideas that the rule is wrong, that it's not orthogonal enough. Why would pattern matching involve cumulativity tests? So we found out that this rule was incomplete while actually trying to prove the completeness of the type-checking algorithm. And that gave us immediately this failure of the proof, an example, an idea of an example to show subject reduction failure in Coq, which we could implement easily. We tried to give a quick and dirty fix to this issue, but if we had implemented this fix in the type-checking algorithm, we would have needed to use a strengthening to prove our meta-theoretic properties on this fixed version, which would be complete, but only if the theory itself admitted strengthening, which is a property that tells you that if I have here a dependent product which is well typed, then I can extract a subterm. For example, here I could extract A from this type, and knowing that A does not depend on Y, try to get a typing for this type in the context gamma, so not extended with Y. So it allows to remove variables from a typing. But that's actually not possible to prove in general in the current presentation of Coq. So a more interesting fix would be to actually fix the information flow in this rule, and that's what we've done. And that's really inspired by the bidirectional presentation of the system. So now this match construct in Coq no longer carries a lambda abstraction to represent the predicate. It rather separately carries the parameters, so A and T here, and a universe instance at which the elimination was done in the first place. It also carries binding names, so the X and E that we use to construct the return type. So these are just names; they don't really matter for the calculus. It's just a way to refer to the binders. So the representation is actually using the Brownian indices. And the new in the new representation, we must now derive the predicate and branch context on the fly from these binding names and the declaration of the inductive type in the environment, which tells us what should be the bindings for the dependent return predicate, and for each of the branches, what are the bindings corresponding to arguments of constructors. With this new rule, completeness holds and reflects actually the user syntax more closely, because as I was saying before, actually when you write a match, you are hiding these lambda abstractions, which some tactics in the system could see. So in the previous representation, a tactic could look into occurrences of subterms, for example, in the bindings of Y and E in the lambda abstraction, resulting in weird occurrences selections in tactics such as change or rewriting. So there would be occurrences in the goal that you could not see ever. Another benefit of this rule is obviously that we don't see cumulativity appearing in this rule. It's completely orthogonal. So there can be a cumulativity happening at a match. You can have a P which is not an object of type EQ at I, but at a lower universe level. But you will just use a cumulativity rule to lift it to I if it's possible. And of course, we get a clear information flow from the bidirectional version. We know exactly which terms we have to infer, and from what information can we derive more information to make to make the rule more algorithmic. So we also have a general bidirectional presentation now of the calculus that are so the bidirectional derivations are completely syntax directed. And they also use compressed and localized conversion rules. So this trivializes correctness and completeness of the type inference algorithm, which mostly follows bidirectional rules, which was a more complex endeavor before when we didn't have this bidirectional representation. A nice benefit from this bidirectional representation is also the principality of typing. So the equivalent of uniqueness of typing derives directly from the correctness and completeness of the bidirectional typing with respect to undirected typing. Just a little caveat is that to prove completeness and correctness, you need some properties on your dependent type theory. So for completeness, you will need injectivity of type constructors, and for correctness, you will need transitivity of conversion. And another benefit is that strengthening now follows directly from the bidirectional presentation, whereas we could not prove it for the previous system. So all of this is work in progress on the correct and complete type checking algorithm for Pickwick. So there was a big impact of this change on MetaCoq, so on formalizing the new system with this more refined rule for cases. So there is a peculiarity in Coq is that we have let bindings in context. So we must carry actually this canonical context for predicates and branches that I've just shown can be derived in general. But in the model, we must carry it around to maintain well-behaved recursive definitions of renaming substitutions and all the operations on syntax, which would otherwise need to rely on a well-formedness argument on the global environment. And this also, in turn, requires to consider only well-scoped terms for the theory of reduction, which was previously valid on even ill-scoped terms. So that's something that we did not foresee when we started the formalization, and we had to adapt all the theory to handle this new invariant on terms. But that's rather useful for other extensions of the system. And now there is an equivalence that we need to show between Coq's initial theory, where we don't store this canonical context, and the Pickwick model, where we do store them, which concentrates all the reasoning we need on this well-formedness of the global environment. And finally, now that we have this canonical context in the branches and the predicates of matches, we also need to expand the let bindings that appear in them as a translation. So we translate from a theory where constructors can have let bindings and branches can let bind variables to the same theory, but in which the constructors are let expanded and the branches as well, which we can show correct using the MetaCoq tools. So some takeaways from this change, which was quite impactful. You should always define a bidirectional version of your system. You've already heard John say this. It will keep you honest. It's really essential for working with the dependent type theory. Another takeaway from our implementation or verification in MetaCoq of this change is that minor implementation changes can rely on subtle abstentions over the theory or require non-trivial reorganizations of the meta theory, which you won't see on paper, but they can no longer go unnoticed if you formalize your theory. So that's a nice benefit of having MetaCoq here. And the overhead of formalizing is quite high, but it can really catch bugs earlier. And this investment on formalizing your meta theory also allows you to test ideas on other extensions in an easier way and a more trustful way. And that's it for me.
Yeah. Thank you. Great talk. So please post your questions in the Q&A tab for the online people. Richard, do you have any questions there?
None here right now.
Me neither.
Perhaps we should we move on to discussions?
Yes, then yeah, let's just thank Mathieu again and move on to the discussions.
Oh, hold on. The student volunteer here says that there's. Oh. It looks like Neil has raised his hand.
Okay.
Hello. I just wanted to ask you, like these changes to the match statement. Do you think they'll have like? Do you think they'll enable any future improvements to the match statement in Coq? Like, will it help you with the equations compiler or anything like this?
So they're already part of Coq since Coq 8.14. They help with efficiency of reduction. You avoid reducing in the type of the binders, which actually are never used. They are also helpful to fix some tactics. So I was saying occurrence selection can have weird behaviors because these binders appeared where they should really not. Regarding efficiency, it's a bit more efficient when you compile. Actually, when you extract and compile through the MetaCoq verified erasure, for example, having branches being expanded like this simplifies a lot. Extracting to languages which already have a version of the match construct, which usually don't expect the branch corresponding to a constructor to be a string of lambdas corresponding to the arguments. They'd rather have a direct way to reference to the argument. So this helps also in that regard. Yes.
Okay, thank you.
Okay, yeah. Then let's move on to the